promoting the advancement of computer graphics and interactive technology in Asian region. And this year, as you know, AsiaGraphics starts to launch a new form of online web seminars we call AG webinar. And the purpose of the webinar is to showcase exciting research results and inspire and motivate new research for the AsiaGraphics community to meet and exchange ideas. And this year, as you know, AsiaGraphics was founded in 2015. And the founding chairman is Professor Wenping Wang from the University of Hong Kong. And from this year, the officials have been reorganized, and Professor Shimin Hu from Tsinghua University, China, is now the chairman of AsiaGraphics. So before our AG webinar begins, so let's have Professor Shimin Hu to make a short welcome speech on behalf of AsiaGraphics Association. So please, Professor Shimin Hu. Shimin, so you can, we can't hear your voice.
Okay, hello.
Okay,
can you
so,
see my screen?
Yes.
Okay.
Yes. Okay, so please go ahead.
So, dear professors, dear students, dear friends, so it's my honor to introduce AsiaGraphics Association firstly. So AsiaGraphics, the full name is Asia Association for Computer Graphics and Interactive Technology. As Li Gang said, it's founded in 2016, registered in Hong Kong, and we have, and this is our logo. So we hope AG could be as well as SICP and Eurographics in United States and Europe. So benefit of founding AsiaGraphics to Asia's CG community, we have three purposes. So cooperative the organization of events in Asia, provision of service to Asia community and beyond, and coordination with other associations of similar interests for exchanges of benefits such as Eurographics and SICP. This is AG organization. Wenping is the founder of the society and he is the first chairman. And currently I'm chairman of the society, and Songyong Li and Hongbo Fu are vice chair, and Li Gang is secretary. We have 23 exec committee. So this is name list. This is members in exec committee. They are from mainland, Korea, Japan, Taiwan, Hong Kong, Israel, Singapore, and other. I mean international like Europe and United States. And the AG Association, we have three successful conferences. The first one is AsiaGraphics. AsiaGraphics is founded in 1993. The full name is Pacific World Conference on Computer Graphics and Applications, founded by Professor Kuni and Professor Shin from Korea. And currently, the steering committee chaired by Professor Songyong Li. As you know, all papers of AsiaGraphics will be published in Computer Graphics Forum as a special issue. Last year and this year, AsiaGraphics is in Wellington, New Zealand. Unfortunately, due to pandemic, so it's online conference. The second conference of AG is GMP since 2000. The full name is Geometric Modeling and Processing, founded by Professor Myung-Soo Kim and Wenping Wang, following a workshop in 1998 in Seoul. Wenping know more details. And the steering committee is currently is chaired by Kai Horman. And the proceeding of the conference is a special issue in CAGD journal. GMP 2021 this year is in Pleasant, Czech Republic. Unfortunately, is also an online conference. So you can see previous conference. Actually, before 1914, it's binational. I mean, every 2 years there will be a conference, not every year, but after 2015, it's every year conference. And the third conference under AsiaGraphics is CVM since 2012. It started from 2012 in Tsinghua University, and all CVM papers are published in 4 journals, include IEEE TVCG, Graphical Models, JCST, and the CVMJ. This year, we have already organized the 9th conference, and next year, CVM will come back to Tsinghua, Beijing, and we will have 10-year celebration. And the AsiaGraphics Association, we have Age Award. We have three awards. The first one is Lifetime Achievement Award. Professor Nishita and Professor Shin won the award in 2017 and 19. The second award is Outstanding Technical Contribution Award. The winners are Baining Guo, Hu Junbao, and Tako Igarashi. The last one is the Young Researchers Award. Winners are Nobuyuki Umetani, Ruizhen Hu, and Lin Gao. We just finished the call for nomination of this year, and the award committee is selecting new winner of this year. So now we will to promote graphic research and development in Asia. We start a new event we call the webinar. So we hope to meet and exchange ideas regularly. So this Li Gang's idea. So we showcase exciting research results, inspire and motivate new research, and create a recurring opportunity of communication and operation. And for the AsiaGraphics community, also we hope for available for other community. So thank you, Li Gang, and we hope this event will be very successful. Thank you.
Okay. Smin, can you make your screen sharing? Okay, so yeah, sorry, my network is does not work just now. Okay, so you can hear me, right? Okay, yeah. Yes. Let me share my screen again, and I will give a very brief introduction to our talks. So thanks, Professor Hu, for the nice introduction on AsiaGraphics as well as the AG webinar. So this evening, we will have 2 talks, and are honored to have 2 speakers, Professor Wenping Wang from Texas A&M University, USA, and Professor Nobuyuki Umetani from the University of Tokyo, Japan, in our first session of the AG webinar. So we will start from the first one. So Wenping Wang, I believe most of you or everyone knows Wenping quite well. So he is a co-founder of AsiaGraphics and motivated the founding of the association. So Wenping Wang conducts research in computer graphics in many areas, including geometry, vision, robotics, and medical image processing, and many has published over 117 journal papers. He is a journal associate editor for many journals like CGD, CGF, and the IEEE TVCG. And he is an IEEE fellow and had won many awards, including the China Graph Outstanding Achievement Award for China Graph, and the John Gregory Memorial Award for contributions in geometric modeling 4 years ago. So let's have Professor Wenping Wang to give the talk. The title of the talk is Studies on 3D Reconstruction. So Wenping, please go ahead.
Thank you, Liga. Thank you, Shimei, for your introduction to AG and also my presentation. Now I'll share my screen. Can you see my screen?
Yes, okay, go ahead.
All right, so I guess I have about 40 minutes, right?
Yes. Yes.
Okay, thank you.
Please go ahead.
I'll finish this up. Actually, there will be two parts in my presentation on studies on 3D reconstruction. I'm from now currently Texas A&M University, and at the same time I'm on leave from the University of Hong Kong. Let me see how to move. All right, the first part of my presentation is implication of visual computing in archaeology. More specifically, I will discuss a system and methods we have recently developed for fast imaging and 3D reconstruction of archaeological sherds. Sherds means those fragments. Okay. It is well known that computer graphics in general has been applied to archaeology in many different ways. For example, we can use computer graphics to model 3D objects in archaeology. We can perform digital restoration for consumption in virtual reality, and also to provide a virtual environment for archaeological simulation. But today, my presentation is focused on using computer vision or 3D reconstruction technique to acquire 3D models of these archaeological fragments or pottery fragments. Another name for these fragments is sherd. So fragments, pottery pieces, and sherds, these terms will be interchangeable in my discussion in the following. Well, these fragments are most common artifacts you found at archaeological sites. They are very useful since they encode our human past. The task is how to get digital models of these fragments and for documentation, analysis, and resampling purposes. This task is very challenging for several reasons, mostly because they come in different shapes. They're very thin. Normally in a day at a typical archaeological site, you would uncover hundreds or thousands of such pieces. Therefore, the speed of scanning this object is important. There are mainly two ways of scanning these sherds in terms of how you place it. I would call these two different ways, standing and lying down. On the left is a standing mode. That is, you use some object to hold it up, to make it stand up, then use some scanning device, scan object. Obviously, only part of the object can be scanned because you use a partition, what other object to hold this piece, and that part is being occluded. You need to scan it again. On the right, you can see the pieces are put flat on a board. You can still scan this object, but now you can only scan one side object. Then later you need to flip them over, scan other side. So my point is, it seems like manual operation or intervention is always needed in order to scan these pieces in two passes. Okay, it's hard to make it very fast. Well, this is standing mode. As you can see on the left, you scan it twice. or then you piece them together manually or use some digital tools. This really slows down the process. How can we use this kind of process to scan hundreds of thousands of pieces in high quality every day? So this is a challenge. In the lying down mode, as mentioned before, you scan the front side, you flip them over, you scan the back sides, and with these partial 3D models, there's still a task to piece them, to put them together. We call it registration to get a complete model. But in this mode, there is a potential advantage of being able to scan multiple pieces in one go. So you can put on board, say in this case, 7 pieces. Okay, you could put in more. Well, here is a photo of the actual fragments excavated Armenia this summer by one of our collaborators in this work. As you can see that so many pieces are found every day and how we can process them. Now, you should realize that in many countries, these archaeological objects are not allowed to remove to another country. Therefore, if in the summer you found 100,000 pieces, you have to think of the way to get them out digitally. That is scanning them, because the physical objects cannot be easily moved to a different country for study. All right, here are some related works. In this work, I think the paper appeared in Talk several years ago, and people proposed a laser scanner setup to scan such objects one by one. They are dealing with a similar object, not really pottery or fragments, rather a fresco. That's kind of like a wall painting fragments. The difference is pottery fragments don't have to be very flat. They can be curved surfaces, but fresco fragments are always flat and have constant thickness. The throughput is not very good. It's only like less than 100 fragments can be scanned every day. There is another system proposed a couple of years ago with even a lower throughput. They can scan 40 pieces every day. These objects are more general, but manual intervention can be expensive. Okay, now, I said that there are typically 2 ways of holding the objects, standing up or lying down, but people always are creative in this kind of situation. In this particular work, the system is proposed that this object can be held in this way, using some pinches, or you can hand them around or hold them up. Yes, the system now allows the scanning in one batch, multiple pieces, but the manual operation involved in moving and putting the objects in place can be more expensive. Again, the throughput is less than 100 per day. There's yet one more related work coming from the group in Princeton. They developed such a hardware setup with a board that put multiple fragments on board so they can scan it in multiple pieces in a batch mode. Potentially can be slow, but so far this system achieves only 22 segments per day, mainly because they have only one camera. The camera need to be moving around. The path planning of the process can be very time consuming. Another problem I will mention later is when you have multiple pieces scanned together, front side, back side, so later you need to figure out which front piece should match which back side in order to find these individual objects. And that was an outstanding problem, as in this paper are stated. Let me check my time. All right, now I'll come to the presentation of our system. We have achieved, we have developed a system that achieved a very high throughput, over 1,000 pieces per day. That is all within 8 hours. And our system is not only able to scan these pieces very quickly. We'll also present a 3D reconstruction pipeline to turn these scanned images into complete 3D models as you can see on these slides. The accuracy we can achieve is about 0.14 millimeters, and easy to use the interface, and it is can be deployed in actual excavation sites. As a matter of fact, this past summer, our system has been deployed already in Merinia, and it achieved all these benchmarks. All right, this is an overview. Our system has two parts. First is a device that can quickly acquire images of all these shards, and another system, which is the software pipeline that is responsible for converting the scanned images into 3D models. Now, look at the first part. This is the hardware setup for image acquisition. There are several pieces you can pay attention. I'm not sure you can see the mouse. Here on the upper left, we have 3 cameras mounted on a supporting system. At the lower right of the system, there is a turntable which holds 9 pieces. In this case, the turntable can turn around. It emulates situation like putting objects there and allow the camera to go in full circle, take images. So we have 3 cameras. How many images will take? In one full circle, there are 16 stops. So therefore, the total number of images we use is 3 times 16, 48 images for one side, the front side. And then later, these pieces will flip back over, and there is another go to complete the scanning process. Now, this is the basic idea. Okay. All right, next. Once we got the images, what about 3D reconstruction? From left, as you can see that, suppose we have scanned the front sides of the 9 pieces and back sides. Now, first, we perform image segmentation, and then using the mask, we can get a partial reconstruction of the front side and back side. They're partial because the other side is always occluded. And the next task is to match all these 9 front sides with their correct counterparts. So which other back side should match? Okay, as you can see that they look different. We need to find out. Well, if you don't want to do it manually, you have to develop an algorithm to perform the right global matching. Once the matching is performed, in the lower right corner, we have to perform a 3D registration like ICP to put them together. I will explain the details one by one. All right, first, of course, is the segmentation. We develop our own segmentation methods. That's a simple task. We use open MVS and off-the-shelf software to perform this partial 3D reconstruction. Okay, the other side cannot be seen. And then we have front side, back sides. So how to match them together? Okay. For each 3D piece, we assume it's relatively flat. We can get a 2D contour. Using these 2D contours, we identify which pairs should be matched together. As you can see here, so now P0 should be matched with Q1, and P1 should be matched with Q0, and so on and so forth. So we don't want to match the wrong pairs, and therefore, if we have a correct, okay, so how to match them? That's an interesting problem. So now we reduce matching problem to the problem matching 2 objects, but each one is a 2D closed shape represented by polygon. For each 2D polygon, we can compute a so-called length and angle profile. That is, when you march along the boundary of the shape, you can always record the length you have traveled and the angle you've turned. This profile showed on the left lower corner. If 2 profiles can be matched together, then the corresponding 2 pieces should belong to the same object. Otherwise, they should belong to different objects. Okay, the idea is very simple. It is very effective. Once we have the correct pairs matched together, front side, back side, we need to consider the registration problem. The registration problem here is particularly challenging because the front side, back side, the large part of that are not common. When you look at the front side, you don't see the back side. but we have to have some common area in order to perform this SICP registration. What is a common area? The common region is just the thin strip along the boundary, as you can see. Okay. Now, on the boundary, you have the red part, the blue part. These points should be extracted and used for reliable registration to get a complete 3D shape. Now, the data set. Let me look at the time. Okay. In order to validate the quality, especially the accuracy of our approach, we have tried to get a data set for validation purposes. For validation purposes, we used 5 completed pots, and as shown on the right, yeah, there are only 4 because we forgot to take a picture of one of them before breaking all these pots. All these 5 pots were broken into pieces, and each piece is scanned with a high accuracy professional grade scanner with a much higher accuracy, 0.04 millimeter. The scanning process is very long. It takes several days, as shown here. And all these 123 fragments are scanned at the ground truth. Therefore, if we later perform a fast image reconstruction, we will always compare with the accuracy in the data set and see how accurate our fast system is against this ground truth, Okay. Now I'll show a video about 40 seconds. You can appreciate how the system works. By the way, I should mention that our special design allows online real-time preview of the reconstruction quality. If anything goes wrong, we don't have to wait for a long time. We can repeat the process right away because our reconstruction process is very fast, allows this interactive operation. Of course, this video is accelerated by 6 times. All right. Our system already achieved the throughput. Throughput meaning how many pieces you can scan in one day, about 1,000. But later we found even more effective ideas to make this faster. That is, we can use this very simple idea. We can use 2 boards. While the first board is being scanned, we can use the second spirit board to put the second batch of objects there, and without letting the system waiting for the human operation. Okay, so this will save some more time to increase the throughput to over 1,200 pieces per day. All right, this is the actual situation of deploying our system in Armenia. Our people were working here, finding 100,000 pieces every day, put in big boxes, and so on and so forth. Okay, this has been tested, so we achieved this performance. Some more details about the system performance. We performed the throughput test, the accuracy test. Then there is one thing I want to mention. The state of art of our MVS reconstruction is about 1:200, and we use a similar setting with more optimized setup. We achieved our similar accuracy is 1/400. I will not say this is too much, but I want to point out the accuracy achieved by our system is around or slightly better than the state-of-art accuracy if you use our MVS, open MVS. And the limitation now is the pixel size. Okay, so you can never be more accurate than the size of a pixel. All right, here I hope you can see animation, the video on the screen. Ligang, can you see this video on screen? No.
Yes, I can see the video.
These are the reconstructed pieces without texture and with texture. So they are not really flat pieces that can be very challenging. That can all be handled by our system. These are reconstruction models. All right, there are some detailed comparison and ablation study. I will not spend too much time here. I want to mention several things. The first question is, okay, we use 3 cameras, but why not more? Why not fewer? Yes, we tried different numbers of cameras, use 1. As you can see on the left, C1, this is the angle, 2 cameras, 3 cameras, or use combinations of their numbers and positions. And in the end, we found that, well, three cameras use 3 cameras using 3 cameras does bring in the benefits of better accuracy, and we can afford it. Each camera cost several hundred US$. The whole system set up, including supporting system, a couple thousand US$. So it's not quite expensive compared with the other existing systems. And another question is how many images we should take. Now, in our current setup, we take 16, we have 16 stops in one circle. Time 3, we use 48 images. Taking more images would mean slower time, potentially more accurate. But our ablation study shows that the 16 images will be good enough. And more images will not bring significantly more benefit. Okay, the scanning batch size can be different. It can be as many as 18, it can be 4, depending on the size and the needs. A system works all right. There are some potential applications, or there could be research direction. That is, if we have all these pieces scanned in 3D models, but how to put them together. If we know they belong to the same pot, then putting them together is a combinatorial problem. The geometric quality shown on the right is not great. This can be a very useful future research problem. And also in our actual situation, we don't know whether all the pieces actually come from the same pot, how to classify them into different pots and still reconstructing the complete individual pots correctly. This would be more research at a higher level of geometrical modeling. Okay, limitations, clearly, when the pieces are very clean without any texture, and then the scanning accuracy, reconstruction accuracy can degrade. And this we can, well, so far we are not doing anything. We rely on original weak texture. There are some possible solutions in the literature. Okay, this is the end of my first part. I will not spend time to go through conclusions. For the sake of time, I'll quickly move to the second part of my presentation. It's also 3D reconstruction of surfaces, but of a very different flavor. It's not about application. The main idea of the second part of research is how to use neural volume rendering, a very popular and up-to-date research technique, a very hot one, for clearly our surface reconstruction. I will share with you a story in the next few pages. All right, so at the present, the implicit neural representation is very research active. It is a very hot research topic. It can be used for image compression. It can be used to represent 3D models. Neural rendering is now widely used for normal view synthesis. I think, do I have? Yes. Here is a typical pipeline for 3D representation from learned from 2D images. On the left, we have a bunch of 2D images. The number could be 40 or even 100. Basically, you need to cover the objects from all the angles. The 2D images will be used to train a 3D representation in a neural network. This 3D representation can be used for novel view synthesis, as you shown on the right, or could be used for 3D reconstruction. Okay, this is the main background. In order to perform 3D reconstruction using this kind of neural rendering pipeline, related works include DVR and IDR. These are all recent works published last year. The central idea is so-called differentiable surface rendering. That is, we can use the input images, simulate camera positions, and finding the camera rays with the potential 3D object surfaces. And the idea is to perform the optimization to change the shape of the surfaces until their perspectives or projections match the input images. So in this process, you should notice that there's always only one single intersection between ray and surface. The optimization process is very local, critically depends on the intersection at this point. This kind of gradient vector is not very robust. So this kind of algorithm have difficulty dealing with our sudden change of depth value as shown on the right. For example, if there is a hole in the object, the real surface to be found is solid black or blue curve, but the camera cannot move far away because it performs a very local optimization process. It can get stuck to give incorrect reconstruction. All right, another related work we want to borrow idea from is called NERF on neural rendering. This pipeline maybe is familiar to some of you. I will not have time to explain the detail to you, but I want to say that the idea is similar in the sense that it learns from 2D input images. It will get the 3D representation, but not a surface, but it can produce very high quality normal view thicknesses as shown here. The representative work here is called NERF, N-E-R-F. And in the middle, you can see high quality normal view thicknesses from various views. I don't think I have a video here. I don't have a video. But what I pointed out, the 3D representation learned by this model, although it looks all right in projection, but actual 3D model geometry is not very good. Look at the right. The 3D geometry is not really high quality as we are accustomed to. This method is really only for good normal view thicknesses. Now, to recap their advantages, disadvantages. But anyway, for surface reconstruction purposes, you can see on the right in the video, there is a huge room for improvement of the quality of the reconstructed surfaces. All right, what is our idea, motivation? Our idea is, okay, if we use surface, we are interested in the surface representation, but we don't want to use surface rendering. But in NERF, we want to apply volume rendering to achieve our surface representation. That is, we want to combine the advantages of the two approaches to achieve high quality, more robust surface reconstruction in our new framework. Okay, our method will be called NEUS, N-E-U-S, is a neural network for surface reconstruction. And before I give you the details, I want to show the advantages of this method, the results. On the left, I showed reference image. Actually, this image can be used for you to appreciate what quality should be expected. The raw input consists of many 50, 40 input images for training this neural network. As you can see that our methods on the right gives much better 3D reconstruction quality compared with the previous works in neural rendering. So what did we do? Here is the pipeline. I want to show. Okay, now the key idea is we want to explicitly represent a surface as a sign-distance function in a volume rendering framework. In the past, there are no such combination. But if we do this in a straightforward way, for example, if you see this red words, the words in red is called sign-distance function here. If we put a sign-distance function here and use this pipeline, it's already some new idea, but it's not much better because we found there is an interesting bias issue if we apply the standard volume rendering framework. Therefore, one particular novelty of our approach is to introduce a new kind of density representation for this surface instead of just using a simple sign distance function. All right, and it's a little bit difficult to discuss the detail here, because it's rather technical. I will give a high-level intuitive explanation. Please look at the figure on the right. It's a very simple illustration. There is a surface, there is level set. T star means location of the surface. And at that position, the sign distance value should be 0. So around the sign distance value, we should build up a density function. This density function is our rho. I think that's a sigma. And then anyway, this red bell shape is a density function associated with the sign distance function. That is, look at the red curve. The maximum point or the peak is at a 0 value of the sign distance function. That is, it is the surface location. But in order to perform volume rendering in a recasting form, we need a weight function W to integrate or accumulate color values along the ray in order to compute the final pixel value. Following the standard or Naïve solution, the green curve, the weight function, has a peak location slightly shifted to the left. This is not good because we want the peak response of the weight function to be exactly the same as red curve, because that means the color value at the peak should have maximum response. The color value should be at the location of the surface, but now it is not. We call this bias. Okay. Now we need to find a method that overcomes the bias to give a more accurate representation. Here, in order to design a correct weight function, there are two basic requirements. Simply, it's called unbiased, which I explained already. The second is called occlusion aware, because in a volume rendering setting, there are often multiple surfaces along the ray. You do not want the surface at the background or behind the front one to be dominant. You should always see the front surface more clearly. Okay, here is what I mean by bias. Look, on the left, the response or the peak is off the top, the surface, that's a bias. On the right is unbiased. When you have multiple surfaces, different surfaces along the ray should have different responses. On the right is occlusion aware, the surface at the back should have lower response. But on the left, that's not correct. All the surfaces have equal response, so you cannot model transparency or translucency correctly. All right, how to get this correct are weight functions. It's very easy to get unbiased functions, but this solution is not occlusion aware. So we're in a situation. We either have a solution which is occlusion aware but not unbiased, or is unbiased but not occlusion aware. Then the details of our derivation is to combine these two ideas together. I will mention just the key results. So on the left is a naive idea. If you have SDF function, sign distance function, the density function used for a correct implementation should not be the bell-shaped function on the left. That is, the maximum value is right at the location of the surface. That's intuitively simple, but that's not correct. The density function we should introduce should be more like a sigma function shown on the right. That is, when the point is outside, you should have some value 0. When the point is inside, the density should be more like approach 1. And the surface location should be aligned with the largest gradient of this density function. So this is the key discovery for a correct implementation of the idea. There are many pages of implementations. I will skip for the sake of time and look at the results. Of course, we need to consider discrete implementation. Since we need to implement it, and here is a simple illustration there are multiple surfaces. In the second row, you can see this zigzag function. There are side distance value. The zero crossing of this blue curve with the horizontal axis, there are the surface location. Then our density function is all with the sigma shape from outside to inside. And at the bottom, the red curve gives us unbiased, occlusion-aware responses, or weight function. These weight functions will be used to combine the voxel colors along each camera ray, perform the integration to give the correct color value. This color value will be used against the input images for supervision purposes. All right, results using the remaining seconds. Here is our 3D in the middle from our input images on the left. In the middle, in the small animation, is the surface reconstruction of the object. And it can also be used for volume rendering, for normal view synthesis if we add back texture. There are more results. We can perform reconstruction with our foreground mask supervision as assumed in our previous works. These are the comparison. In the second column is the quality of our reconstruction compared with other related works. And our method is quite general. It can perform 3D reconstruction without requiring a foreground mask supervision. It can also perform high quality reconstruction compared with not only NERF, but also with the CalMap. CalMap, by the way, is not a neural rendering approach, that basically a method based on traditional MVS, right? And it is not only good for general object reconstruction. In this video, you see the reconstruction of some thin structure using our new method called NEWS, from multiple input images. You can see the 3D objects are, so you have general objects like this is teapot or something like that, or bunny, together with thin structure. All right, we can compare the depth map, the quality of reconstruction compared with NERF or other traditional MVS. No, this is a CalMap implementation. All right, we found that our proper geometric first I want to say some comparison of quality. From left to right, Naïve Solution means using simply put side distance function into NERF framework. There is a bias. The error of reconstruction is 1.68 millimeter, which is not good, but could be better. This human skull has the actual size, about 30 centimeters across. Direct Naïve Solution can be very wrong. The error is about 3 millimeters. With our proper geometric initialization, our full model of NEWS converges relatively fast. It achieves an error of 0.7 millimeter, much better than all the other similar or competitive competing methods. I want to mention the effect of initialization. And for the purpose of training neural network, if at the beginning we have random initialization shown on the top row versus our proper initialization using a sphere-like object, and there's not much additional cost because you assume the object is a sphere and try to improve it, but the effect on convergence speed can be significant, as you shown by this visualization. Look at the cross section, how the zero level set changes during so many iterations of training of 300,000. It takes hours to achieve this kind of convergence rate. For very challenging objects, like Duran, is general objects, highly regular with many sharp spikes. Our method works quite all right. The video here shows the progression of the training process. You can see how the 3D model is being reconstructed inside the neural network. And more results is a DTU dataset. Now, all these reconstruction are based on real photos, but all the input photos or images are posed or calibrated with camera parameters, and these camera parameters are provided together with the dataset. There is another dataset from blended MVS. As you can see that our method is able to show I think you can see the video. Can you see the video now? Oh, it's not moving, but anyway. Okay, it can perform 3D reconstruction and also number view synthesis. Now, finally, some limitations when there are extremely weak texture, as shown in this example, the reconstruction results are not perfect. For example, on that piece of brick on the right, the surface is not reconstructed properly because lack of lighting and texture in this case. All right, finally, I want to conclude by thanking all my collaborators, my students and faculty members at the University of Hong Kong, collaborators from MPI, and particularly Professor Xin Li from Louisiana State University. This concludes my presentation. Thank you very much.
Okay, thank you, Wenping, for a nice and inspiring presentation. So I think we still have a few minutes for the questions. So the secretary of webinar is correcting some questions from YouTube as well as games. So you know, we have audience from YouTube as well as games. Games is a platform, online platform in China. So we have many audience here. Okay, so here's one from Humbo in YouTube. So the question is about the first part. What if the pieces move a bit during the scanning process? For example, due to the rotation of the rotating table. So will it work still?
Oh no, we don't like them moving around because moving around, it's very hard for us to recalibrate the camera. To prevent it, we control the speed of the rotation. We use special material like silicone pads to provide more friction to make sure they don't move at all. And if there is a strict requirement, it doesn't allow multiple tries, then I would recommend use some sticky material, tape, stick them together. But that's not convenient. We tried different approaches. The answer is whatever means you use, and you should ensure that the pieces do not move. Otherwise, the system will not work.
Okay. So
good point, Homba.
Okay, so here's a second question from games. The audience asked, the question is about the second one, the nurse. So the nurse was proposed last year. Since then, there have been lots of works on this direction. So can nurse, so your work, can guarantee the correctness of the topology of the surface due to the occlusions of the geometry?
Well, I think basically these are two questions. First, there are many recent works extension of nerve, and then whether we can get topology. About the first question, indeed, is such a hot topic. There are already hundreds of citations of nerve. You know, many people are working on it, but mostly on different directions. For example, make nerve generalizable, make it work for dynamic objects, large sense. But as far as we're concerned, that is surface reconstruction using a nerve framework. Nerve means not only neural rendering, but a volumetric rendering. There is only one other concurrent independent work on exactly the same task. That is neural volume rendering for our surface reconstruction. That's called volume SDF. And it appeared about the same time of our work, and we haven't been able to perform a comparison, but just roughly compare the work. we think could achieve similar kind of quality. Our second question, whether we can guarantee anything? No, we don't have a theory. That is, it doesn't matter how challenging it is, we produce always our correct result. Why? Not only because this is the complicated pipeline, and this are essentially an optimization process, highly nonlinear, non-convex. So we don't guarantee anything, but from many of our experiments, we found that our system works extremely well, relatively, if you compare with other similar methods. So I would, I think that's a good point. Maybe we should increase the complexity of the objects we test in terms of structural complexity and see to what degree it can still work and how it can fail.
Okay. Okay, there's no other. So the third question is for me. So I remember that many years ago, maybe 10 or more than 10 years ago, there's a work in SICP by Qixing Huang or Helmut Portman, who has done the similar work to assemble the pieces of some objects. So I know the inputs are different. So what's the other difference between your work and their works?
I think these two works are very different. Portman's work and Peter Huang's work are more concerned about how to put the 3D pieces together to form the single large objects. But we're concerned about how to get the digital model of each single piece. And there are basically two different stages of the same pipeline of application.
Okay, so this is your field work, as you mentioned in your talk, right? So
yeah, my talk is like how to get the digital model of a single piece. And sure, but they assume each piece is scanned already. They're concerned about how to solve geometric combinatorial problem to put them together to form the original large single object. Okay, they're related. Okay, yeah, no, but at the technical level, they're different. Yeah.
Okay, I see. Okay, thank you. So due to the time limit, I think we should stop here because there's another talk in the forum. Okay, thanks.
All right, I'll quit. Thank you very much.
Yeah. So Wenping, can you quit the screen sharing?
I stopped already. Yes.
Yes. Okay. So let's start the second talk in our web seminar this evening. So I'd like to introduce Nobuyuki Umetani from the University of Tokyo, Japan. So Dr. Nobuyuki Umetani is an associate professor in the University of Tokyo. And before he came to the university, he was a research scientist at Autodesk Research. Then the primary research he addressed through his studies how to integrate the real-time physical simulation into an interactive geometric modeling procedure to facilitate creativity. And he was the winner of the A.G. Young Research Award 3 years ago. And this is the first award in this association. So the title of the talk is Interactive Design Optimization in Computational Fabrication. So Nobuyuki, please go ahead.
Yeah, thank you for introduction. Let me share my screen. Can you see the screen?
Yes. Okay, go ahead.
Okay. Okay. Yeah. Thank you for introduction, and yeah, thank you for having me in this seminar. So today I'm talking about the interactive design optimization in the computational fabrication. So yeah, about myself again. I'm Nobuyuki Umetani, and I recently become an assistant professor, and I'm now leading my own laboratory at the University of Tokyo. So motivation of today's talk is about the background of computational fabrication. So yeah, recently fabrication devices such as 3D printer and laser cutter are widely available, but the software are still very difficult to use to make some functional objects. So my motivation is make some nice software, interactive, intelligent software to make it easy to design very complicated, especially that involving physics, design involving physics, to make it easy for ordinary people. But usually there is in the complicated design, there is a lot of physics such as strength, sound, electronics, aerodynamics, deformation, and many etc. are involved. So for many years, I have been studying, doing research about how we can integrate these physics into a functional design system. So my principle is simple. Human design some object, but a human and the computer have their own advantage and disadvantage. Human is good at aesthetics and designing usability and considering manufacturability, while the computer is good at solving physics equation and optimizing physical property. So my goal is tightly integrate these human designer and computer optimizer, so that we can bring human into the loop of design optimization. To do so, we have to, the simulation and optimization have to be real time to allow the user to think during this optimization loop. So that's a big challenge. So we solve this kind of problem for many projects, but here is a good example to start with. So this is an example of fashion design. The clothing we wear is actually made out from two-dimensional fabric, cutting fabric and stitching them together, we can make a 3D garment. But the problem is the pattern, that's the cutting shape is two-dimensional, but the clothing is three-dimensional. And it's very difficult to design a cutting pattern while imagining the resulting 3D shape. So there is usually a lot of iterations going back and forth between these procedures. So to make this easy for ordinary people to design clothing pattern, we develop a system to integrate simulation and design. Okay. Let me demonstrate the software here. Okay. So this is a clothing simulation, real-time clothing simulation, computed from this design pattern. So our design system allows an interaction during the editing. So during the simulation. So for example, this tail part, it's penetrating, so we can quickly change the pattern while looking at the simulation. and we can change the design such that the resulting shape looks nicer when it's settled on the top of this armadillo body. We can, of course, cut the dot, and we can also, in the front part, this is a little bit slack, too loose, so we can make it tight by cutting some hole. And we can adjust the size of the hole by looking at the simulation result, that is feedback in real time. And as you can see, we can design a nice clothing that fit into this very complicated shape of armadillo. Okay, that's a demo. Okay, basic idea here is simulation result and design is one-to-one relationship for static analysis. So we can assume that there is the static shape. If we change the mouse position, the static shape changes accordingly. But this function is very difficult to, very time-consuming to evaluate. So instead of we evaluate this function every time we move the mouse, we compute the sensitivity that is linear, that is a gradient of this simulation result with respect to mouse position. And then with linear approximation, we can approximate the deformation linearly with mouse position. And from this linear approximation, we can start a nonlinear iteration to refine the result. That's a basic idea to achieve the real-time interaction for this very challenging physics. Okay, this is another example of free-form musical instrument. So idea is we want to design a musical instrument that have a complicated shape. For example, this is an input bunny shape, and by carving out the internal shape of this bunny and putting the finger hole and mouthpiece, we can design a functional musical instrument. So this is a design. This is a screen capture of the design system. So while the designer change the location of the mouthpiece and mouthpiece, on the background there is a simulation, physics simulation running continuously and predicting the tone of this musical instrument. So the tone says it's a G, but when the user change the scale or moves the mouthpiece, the tone interactively changes. And the user can also place a hole. And when user places a hole, there is another musical note appears. So this musical note stands for the tone when this hole is open or closed. And with this interactive feedback, the user can always look at this where the musical note is currently and change the design to such that the musical notes are the one that designer want. So yeah, here the user changes the size of the hole. Okay. So achieving this real-time feedback for the sound simulation it's very challenging because this is a three-dimensional problem for sound simulation. But here we draw some inspiration from the harmonic oscillation. We use the Helmholtz equation to model the sound's acoustic resonance simulation, and we use general eigenvalue problem in the frequency domain to find the root of this function to identify the resonance frequency. So of course, this is a very complicated, mathematics involved. So if you have interest, please look at the paper. And here is the example of the designed musical instrument. I hope that audience can hear the sound.
Sorry, we cannot hear the sound. Sorry.
There is no sound?
Yes.
Okay. Maybe when I share the screen, I didn't click the button.
Sure. Okay, no problem.
Okay, so yeah, just in case the video fails, I bought the actual ocarina designed with our system. So let me draw it. So this is the sheep-shaped ocarina, and I will play Melissa Resolam. Yeah, so yeah, we can design this kind of stuff with this system. Okay. Okay, let's move on. So designing a shape for 3D printing is very difficult for novice people. So here is one example designed by the novice people, ordinary people, and share it online in the Thingiverse. So this penguin looks cool, but after it printing, this leg part is too thin, and it's broke while I remove the support material. So our goal is real-time weakness detection, structure weakness detection, where the designer interactively designs the shape. The computer analyzes the weakness of the structure and give a feedback to the user, and the user seeking the part, and computer give it a go, and the user can 3D print the shape with confidence. So this is our design system. So in our structure weakness analysis, we can compute the weakness of this dog sculpture in a fraction of a second, and the system detects the weakness and annotates the weakness in the color. So this red shape means when some force is applied to somewhere on this sculpture, this part might break. Same is the legs. And there is no pre-computation of this computation. So when the mesh topology is changed, the system immediately runs another weakness detection from scratch, and immediately feedback the user the weakness of this sculpture. So the idea here is cross-sectional analysis. The structure analysis method we come up with using cross-section. So the key idea is bending momentum conservation. So for example, in this shape, beam-like shape, when we consider the force is applied on the left-hand side and there is a fixed boundary on the right-hand side, and we want to know the stress in the middle, we compute a cross-section where we want to know the stress. And then we compute the bending moment. And in the static equilibrium, the bending momentum you conserve. So there is a counteracting bending momentum in the same amount. And actually, it comes from the stress inside this cross-section. So when we know the bending momentum and the shape of this cross-section, we can compute the stress inside this cross-section. So I'd like to quickly show the live demo of our system. Okay, so suppose we want to print out this sculpture. We are about to print out this sculpture. So we can run the cross-sectional analysis by pressing this strength button. And then without any pre-computation in this very detailed mesh, we can compute the weak part in this shape. And this method is very robust, and actually we can compute the shape compute the strengthness, the robustness of the shape for shapes that have a hole. So in this bunny shape, there is an open hole at the bottom. So typically, people use finite element method to analyze the strength of the 3D shape. And finite element method requires cutting the tetrahedral mesh or some mesh pixelization inside the shape. So if there is the hole in the shape, there is a huge problem. But in our method, we don't need to fix the hole to compute the robustness. Even there is a hole, we can compute the weakness of this shape. This is because we rely on the cross section that can be robustly computed whenever there is a hole in the geometry. Okay, that's a demo. So we talk about the sound and the deformation and the stiffness and the structural robustness, but aerodynamics is one of the most challenging topic in engineering design. Aerodynamics have a wide range of applications such as aerodynamics and car design, but it's still a very difficult problem. And typically, the computational fluid dynamics or CFD is used to find out the performance of the 3D design. So the input is shape and the output, and also the physics parameters, and the output is the force and the pressure field and the velocity field. And in CFD, people people solve Navier-Stokes equation to compute the output from input. But this takes a lot of time because we have to first construct a discretization of the domain, and then we have to iteratively solve this Navier-Stokes nonlinear equation. So instead, we want to replace this. We may want to replace this time-consuming solver with a machine learning model to make it fast prediction. But this is also a very challenging topic because machine learning typically require very consistent parameterization. So that means input shape have to be parameterized into fixed dimensional vector, and output shape also have to be parameterized into consistent vector. So, but this is very challenging problem. So we solved this problem for 3 different projects. So one is interactive airplane design. So that's the idea is novice user sketch the shape of the airplane, and after it fabricated is using the interactive design system involving the physics simulation, and we can fabricate easy with laser cutter. So here is a design system. So while user sketch the shape of the airplane, the system continuously runs the simulation of the flight trajectory. So this is a trajectory computed for 6 different launching conditions. And so user can get always feedback how this airplane fly. But as you can see, designing a nicely flying airplane is very difficult. But there is no problem. So when we press this make it fly button, the interactive optimization start to run on the background and makes optimize the design of the airplane such that this airplane always fly. So user press this button and undesirable trajectory will be nice. But and as you can see, there is automatic adjustment in real time while user changing the design. So user can focus the design using this optimization. Okay, here is one example of the airplane designed by our system. So this is an airplane designed for armadillo. And it flies very well. And we performed many user study to check our idea. And the most interesting thing for our approach is we rely on machine learning instead of fluid simulation to make the real-time design optimization possible. So CFD simulation and especially optimization is impossible to run in real time while user design. So we use machine learning. So here is a setting. So we made a lot of sample airplane and fly them many times and track the trajectory. And from the trajectory, we construct a machine learned model to quickly predict the flyability of the airplane. So this is another project of measuring aerodynamics of falling object. So here, instead of the airplane, we fall down object, lightweight object, and record how it falls down into a single camera. And we track the trajectory of the marker, and we reconstruct the 3D motion in the air of this falling down motion. And then from this 3D motion, we compute the acceleration in the translational and rotational acceleration. And also from that, we compute the force, aerodynamic force acting on this object. And we reconstruct the aerodynamic force acting on this object. So this representation of the aerodynamic force means for example, this arrow stands for if the object is moving in this direction in the air, there will be a force in this direction. So, and our omnidirectional aerodynamical representation can represent the force that is falling down in all the directions. And in our model, using our model, we can represent the falling object for many sizes, and we can also change the weight of the object, and we can also change the density of the object. So the object behavior changing from falling in the air to falling in the water. And we apply this model into the kite design. So here is the kite design interface. While user designs the kite, the stability of the kite is shown in the design system. And we successfully design a flyable kite that is non-symmetric and it's not trivial. And also, yeah, this is an example of a Stanford bunny shape flying kite. And we can measure like this white box and this heart-shaped form aerodynamics of both, and then we design optimize a configuration of these two objects to make this object fly. Okay, as we say, the three-dimensional parameterization is very difficult comparing to the parameterization of the image. So we come up with mesh representation for parameterizing shape. So the idea is we deform the quad mesh, template quad mesh into an input shape, and its deformation encodes the 3D shape. So it's a little bit different from volume representation, and that we use mesh. For the surface representation, mesh representation is more lightweight and it's continuous. So it's good for regression purpose. So this is an example how we compute, deform the template mesh into the input mesh. So we first place template mesh to the bounding box of the shape, and then we project the corner vertices of the template template box. And then we project, subdivide and project the subdivision vertices onto the 3D surface. And then we iterate this subdivision and projection procedure until we reach certain subdivision level. And then this deformation from template mesh to this projected mesh, this will encode the shape. So we put our model into our encoded shape into the autoencoder, and we can encode the shape into 10-dimensional function. And also we develop some interactive system to explore this 10-dimensional design parameter. So having the voxelized template mesh helps constructing a parameterization of the field. So while we deform this template mesh, try to fit into the surface, we can together deform the meshes around this template mesh. And then we can parameterize a field outside this object. Using this technique, we can develop a 3-dimensional aerodynamics prediction system that predicting the aerodynamics of the car, that includes the flow over the car and pressure on the surface of the car, and also the CD value. CD value stands for the coefficient of drag that encode the aerodynamics efficiency of this car shape. And this prediction is instantaneous. We can predict the shape in fraction of second. And the important thing is, in this machine learning model, we can also predict the accuracy of the machine learning model. So that means the CD value here. So this gray range stands for how much the machine learning can be off from this prediction. So this is very important for real-world engineering, because machine learning is not always perfect. So the engineer cannot trust the machine learning unless the machine learning tell you that there is how much accuracy in the predicted model. So yeah, for the real world application, this error range prediction is very important. And we have accuracy that is reasonable in the real world engineering. And actually, after I did this work, I collaborated with the actual automobile company, and we successfully designed a prediction design tool. Like we successfully, developed some prediction to aerodynamics efficiency prediction tool for 3D, car shape, and it's actually now in use for real world, car production. Okay, as a conclusion, so we develop, we tightly integrates the knowledge from the mechanical engineering numerical analysis and the interact technique to make possible the integrated design and simulation and interaction to to make a functional object interactively and try to inspire creativity for the novice user in the coming the age of the personal fabrication. Thank you very much.
Yeah, we have lots of works and lots of videos in this work, in talk. So let me see what questions are raised from the audience. Okay, here's one. An audience is asking what's the CD value in the work of CFD? Does this measure the accuracy error of the results?
Sorry. So CD value stands for coefficient of drag. So actually, this stands for how much the drag force, the force, the car get from the air when the car is moving straight. So
okay.
this force, this coefficient stands for how much the force, the drag force, the resistance force, air resistance, the car will get from the air. And if it is small, it's nice, but it's extremely difficult to make this number small. And actually, many car designer try to make this number small while the car looks stylish. So that's very challenging because if this number is small, all the car looks very dull, like not stylish. So that's why we need an interactive design system. So interactive design system allows the designer to quickly know what the value is without running the CFD computation on the supercomputer. And then the designer can explore the stylish shape while this coefficient small. Okay, I hope this answers the question.
Okay. Okay, the second question is for the machine learning based CFD or something. So how did you make the training sets for the machine learning pipeline? I
made this training set by myself. So I use my training set is based on the shape data set called ShapeNet. So ShapeNet contains thousands of car shapes, and I picked the 1,000 car shape that looks reasonable for the ordinary, not so extraordinary as the car. So ShapeNet sometimes have a broken car, or like car that just have a box, like not so realistic car. So I picked the realistic looking car, 1,000 cars, and for these cars I constructed the tetrahedral mesh. I developed the mesher, like the tetrahedral mesher. I developed by myself, and I ran the Navier-Stokes equation based on finite element method for these 1,000 shapes. Also, yeah, the Navier-Stokes solver I developed when I was a student, and then I collected these 1,000 data and that's how I prepare the training data set. So the training data set is available on my website, so you can find.
Okay. Okay, there's another question about the cross design. I think this is the first work in your presentation. So the question is, the key to do the real-time cross design is the differentiable simulation. So
Yes.
how did you make the collision detection, which is very hard for
Yes,
to
yes,
be
very
differentiable?
nice topic. Yes, yes, yeah, very nice question. Yes, so at this time, differentiable simulation was not a hot topic. So I just call it sensitivity analysis. But maybe, yeah, in this today's phase part of the differentiable rendering or differential simulation, we have to call it differentiable closing simulation. Yes, but yeah, for the collision detection, we need to handle the collision, of course. And collision is difficult when we consider friction. But when we compute the collision, when friction is ignored, it's simple. We just assume that there is a strong spring in the normal direction and try to prevent the penetration of the point from the object. So these normal spring can be linearized, and we can compute the sensitivity. And we can unfortunately handle a case that's a new point, come into contact. That's a very difficult problem. So yeah, that is what we miss in the linear approximation. But as long as the sensitivity mode that doesn't penetrate, we can handle by modeling the like a normal modeling collision as a normal spring. Okay, I hope that's the answer.
Okay. Okay, so I think, okay, there's the last question, I think, hope so raised from the YouTube audience. So the question is mentioned as this: as far as I understand, you have tried to replace physics-based simulation with neural network trained with a lot of data. So the question is, what is the scale of the data set required to achieve satisfactory results?
Sorry. So my slide was very confusing. I didn't use neural network at all for this regression program. So I used Gaussian process for the CD value, like aerodynamics problem, because Gaussian process doesn't overfit, even if the data set is small. And also Gaussian process will predict the accuracy of the prediction. So the one big drawback of the neural network is it's very easy to overfit. And to prevent the overfit, one have to prepare a lot of data set. And in this machine learning, it's very hard to prepare so many data set. So and also it's very hard whether a model is over. It's very hard to know whether the model is overfit or not. So that's why I use Gaussian process. So in this card CFD program, the data set is 1,000, and that's enough for getting a nice accuracy. And this airplane, we constructed, like 13 different airplane, and we launched hundreds of time, take sample hundreds of time flights.
Okay.
Okay.
Okay. So I think you have answered the question. So just a mention for this question. So generally, people are tending to use a large-scale neural network. So
Yes.
maybe hundreds and thousands data training data are not enough for this kind of large network as well. So as you mentioned that this is leading to overfitting stuff. So maybe this is a very serious issue in this kind of direction. So what are your points on this? So just a mention, just a comment.
Yes. So yeah, using a neural network for regressor is as far as I know, very tricky. It's also very difficult to train. So for this problem, I intentionally avoid use of neural network for this problem. But maybe in future we can there is a lot of new technology such as Fourier future. That Fourier future use sine encode the input into like sine function and cosine function, and it's overtone, and that's a magic technique that to make the regression problem much easier. So maybe in future we can come up with similar problem that's transforms the input into another dimension, like more larger dimension, and then we have some the network to predict the model, right? But that's a future work. As far as I know, physics phenomena is very complicated, so it's still very hard to express it in neural network. But it's a very, I believe this is a very nice future direction.
Okay, so I also agree that the differentiable rendering or simulation can stimulate our future works a lot. So, okay, I think there's no any other questions from the audience now. Okay, so let us stop here. Okay. Okay.
Thank you very much.
Thank Nobuyuki Umetani for this nice talk, and this end the webinar of this AsiaGraphics Association this evening. So let us thank both speakers, Professor Wenping Wang and Professor Nobuyuki Umetani again, and thank you so much for this nice talks and this, for this the first webinar in AG. Okay, thank you.